Okay, hello and welcome to the theory of operation video on this discrete 7-level ADC kit that I put together. This is a pretty neat little project. It was kind of fun to work on. I'll just walk through the basic operating principles of this. There are many kinds of analog to digital converters. This is kind of a simple architecture that we could build and maybe understand in a relatively short period of time, that's based on comparators and a ladder, a resistor ladder that provides a bunch of reference voltages. More commonly, you'd use something called a successive approximation ADC. There are other kinds that you would usually see in these more complicated integrated circuits. But this does a nice job of illustrating kind of the working principle of what could be going on inside one of these. So what's going on in this board is we just come in to USB micro for a approximately 5-volt supply. It goes to this power switch to this power indicator. You'll see 2 resistors by that LED. I used 2 only because I wanted to use 1 value resistor for the whole board, just to make that easy. So I used 2 resistors in series to make 1 large resistor, so they're all the same. That's all that's going on there. So we light up that resistor, and then this 5 volts goes on to power these integrated circuits, and it goes to this potentiometer. This potentiometer taps off of that 5 volts, between 5 volts and ground. It'll tap off anywhere between 0 volts to 5 volts. And it feeds that down to this VN path, which you can kind of see drawn on the schematic in the silk screen in this board. And this VN path feeds to one side of these 7 comparators. What a comparator does is if the input voltage is below a reference voltage, the comparator output is low. If the input voltage is above the reference voltage, comparator output is high. So a comparator, it just subtracts these voltages, basically, the 2 inputs of the comparator. Positive, high, negative, 0 volts, low. So that's what's going on there. So you've got this input voltage which will range between 0 volts and 5 volts that gets fed to all of these comparators equally. Now we also have a supply voltage coming into this reference voltage integrated circuit. So this is a 4.096 volt reference voltage. So you can put in whatever you want kind of coming into it. It's going to kick out about 4.1 volts. So coming off of that 4.1 volts, it feeds to this VREF test point there, and it comes down to this resistor divider. And it divides it down. These are a bunch of equal value resistor. It divides it down equally and feeds in sequentially increasing voltages to these different comparators. You can see them written down here. This is approximately 0.512 volts, 1.024, 1.536, etc. So each of these comparators has an increasingly higher voltage. So what happens when we turn the potentiometer and increase this input voltage, once that reaches above 0.512 volts, that comparator goes high. We continue to turn the knob, it increases above 1.024 volts, that comparator goes high. Keep increasing the knob, and as you increase it, and this voltage gets higher and higher, it's going to turn on one after another, after another, after another, after another. And we can see that here. I'll turn this counterclockwise, and you'll see each LED in sequence turn on. All right? So that's what's going on there. So a simple series of 7 comparators, a reference voltage, a ladder string, a resistor ladder, and then a reference voltage to compare against. So out here we've got bits 1 through, I'm calling it bits 1 through 7 here. Then we go from there to encode it into an actual binary form. Right, and binary is how most computers will do signal processing or store numbers. Something like 100 is, what is it, 124. 010 is 2. 111 is 7. So we take this series of 7 individual digits, zeros, and convert it into a binary number, a 3-bit binary number. Hence, it's actually a 3-bit. By the time you get out here, it's 3 bits, though it's a 7-level ADC. And you can see it convert the increasing bits here into actual binary number here. Do this so you can see it. So you see first bit goes on, you increase the second bit, then both, third, etc. So you get a binary 0, binary 1, binary 2, 3, binary 4, 5, 6, and 7. And then the output of here, you've got your binary number. So that's how this is operating. Inside these two ICs was just a bunch of comparators. Inside this IC is just some digital logic. It's relatively straightforward digital logic to just encode these into that. You can even do that discretely. It's actually not that hard to do. It's a bunch of transistors and diodes doing that. Or you could do it that way. That's not what's inside the IC. These resistors are just here to limit current into these diodes, and again, you use two of them, you only need one, but just use the same value resistor all over the board. And that's pretty much it. So that's how it works. It's a basic working principle here. Again, different analog to digital converters. They do this in different ways. There are a lot of different ways to do it. Each has their own pros and cons. Things, if you wanted to take this to a next level, you could look at is things like accuracy. You can look online at data sheets or look at explanations of A to D converters, and there's linearity, monotonicity, there's the accuracy of how well does a bit correspond to any particular voltage. If you went in and actually started to map that out and graph it out, you'll see areas where this works pretty well, and you'll see areas where it doesn't work very well. And then you could look at this compared to other methods, and what are the pros and cons of that. You could also say, hey, if I wanted to improve this, you see something about this that isn't so good, right? There's something that's not very precise or not very accurate. You might think about how would you improve that and how would you make this a little bit better and learn about that. So you can spend quite a bit of time if you wanted to learn different things about analog to digital converters in general and this type of approach specifically through this kit. So again, we've got the kits in the store. We have a build video that'll walk you through building it and debugging it. So if it looks interesting, I hope you pick one up, build it, and have a good time with it. Thanks for watching.